So as you have seen, we have switched to first talk because a lot of what I wanted to explain was in fact explained already by Caitlin. So then there will be many slides where I will go very fast because this will be more repetition of what you said just before. But then what is good is that by skipping some of these slides, you will give me probably enough time to show one process that maybe shows that bubble accretion is not working, so which is fun because bubble accretion was invented to solve one first problem, and then we now may see that it is not working, so then we have to work again. So we are far from unemployment. So okay, so this is what I will discuss now. So I will just start with some introduction on exoplanets and population synthesis. Then I will show that I will then discuss what I call integrated models, which is not population synthesis, and then I will go to population synthesis model per se. And then I will try to show some of the prediction of these models and also how they can be used to predict or to compare with microlensing, future microlensing results. And then, if I have time, I will go at the end to this pebble versus planetesimals and trying to show how, in fact, it's not so simple to explain planet formation with pebble accretion. So let's start by some introduction of planet formation model. So as was already explained, so planet formation model try to explain how we go from a disk to planets. So this is a diagram where you have a mass of a planet in the log-scale Earth masses, and here the semi-major axis. And what you see is that we have 4 orders of magnitude on the mass, 4 orders of magnitude on the semi-major axis, so planetary systems are very diverse. So what we try to understand is, can we explain this diversity? How can we explain this diversity of exoplanets, and how can we predict the properties of some of these exoplanets? So something that is very important that people maybe they don't really realize all the time is that all the data we have on exoplanets use some stellar evolution models. And I think that's quite important because just an example here, again, this is the same diagram, this is the mass, but in fact this is not the mass of a planet. This is the ratio of the mass of a planet to the mass of a star. So you need to know the mass of a star if you want to know the mass of a planet. And this is the distribution of radius of planets from Kepler, but again, this is not the radius, that's the ratio of the radius of a planet to the radius of a star. So you need to know the star, otherwise you don't know a lot about the planet, okay? So why is it important? It's important because, okay, you need to know what is your star. So how do you know what are the properties of a star? You use a stellar evolution model. So basically, there are 2 ways you can do stellar evolution. One thing is just take a sphere of gas and then you just solve the hydrodynamical equations and then you evolve this. But practically speaking, this is not possible because this is too time consuming in terms of computational power. So what people do is that you use stellar evolution models, which are simplification of the real hydro models, equations. And so basically, so these are probably the equations that you may have seen during some classes. So these are stellar internal structure equations. So these are 1D equations. And what you do is that you start with a 1D description of your gas ball, and then you evolve it with time, and so you have this kind of diagrams where you have the log of the luminosity of a star versus the log of effective temperature. So, for example, a 4 solar mass star will follow this kind of very strange track. So, okay, this has nothing to do with planets, except that in fact these equations are the same as the one we use to solve for internal structure of planets. But what is very important is that so if you combine this evolution model with some distribution of, for example, of initial mass of stars, then you can do synthetic HR diagrams like these ones. And this is a population synthesis for stars. So what I want to show here is that population synthesis needs 2 different things. The first is what I call integrated model or evolution model, here in this case of stars. And the second thing that you need are initial conditions. So I think it's important because very generally speaking, people in general, they tend to mix, in the case of planets, population synthesis and integrated models. And these are 2 very different things. Population synthesis is just running the formation model of a planetary system with many different initial conditions. So let's move to planets. So I will go very rapidly. So because this was explained before. So so now how can we compute the formation of planetary system? So we know that okay, we start planetary formation is a result of stellar formation. We have a cloud, we form a star that you can see here, and then by angular momentum conservation, we form a disk. I like this image, although it's a very old one, but okay, this is an image of a disk. And then here we form planetary systems. And what we try to do is, again, to understand this transition from disk to planets. And finally, this one can be observed by, for example, WFIRST or any other way. So, okay, so as was mentioned before, we have two ways to see planet formation. Top-down model and a bottom-up model. So this is the co-accretion model, the old co-accretion model. And this is the disk instability or gravitational instability model, which, as was very well explained just before, is probably not the way to go to explain formation of planets, in particular of flow mass planets. So I skip this. This is just explaining what you have said, that it's difficult to explain formation of planet with disk instability. And then I go to the co-accretion model. So I will just explain again what was said before, just to be extremely clear. So in the co-accretion model, you form a planet in two stages. You first have formation of a core by accretion of solids. So solids, will come back later. What are these solids? But so you accrete solids and then you form a core. And then when the core is massive enough, you accrete gas. And this massive enough means around 10 Earth masses, although it can be smaller in some cases. So you see that you have two issues here. You need to have enough mass to reach a critical core mass. So these 10 Earth masses of solids in this case. And you need to accrete this solid fast enough because you want to reach the critical core mass before the disk has disappeared. Otherwise, you cannot accrete the gas because there is no gas anymore. So if you are in a region of a disk where there is enough solids and you accrete them fast, then that's fine. You reach a critical mass before the disk has disappeared, and then you accrete gas and you form Jupiter. If you're in a region of a disk where there is enough mass, but you accrete the solids slow, then you reach this critical mass late, and then there is not a lot of gas to accrete, and you form something that is maybe something similar to Neptune. So a planet that has some gas, let's say 10% of gas in mass, but which is dominated by the core. And then the last case is you don't have enough mass to reach a critical core mass. So in this case, you form something that is without gas, something maybe like a terrestrial planet. So this is very broadly this idea of the co-accretion model. And so as was explained before, one of the main question that is now studied is what are these solids that form the core. So you have basically two classes of model, planetesimal-based model, old, pebble-based model, new. And so they differ in in some aspects. So what they have in common is that you grow solids from small to big. And so in the planetesimal-based model, you assume that going from dust to pebbles to planetesimal is very efficient. So basically, you convert a lot of the mass that was initially in dust in planetesimals. So the mass is in planetesimals. And in the pebble-based model, you have a few planetesimals that are formed, but the majority of the mass is in pebbles. Okay? So this is two different classes. Either you assume that there is a lot of mass in big objects or in small objects. So I will come back at the end of my talk on these two models, trying to see how they can work one and the other. Okay, so when you want to explain planet formation, what you have to play with are two things: a disk of gas and some solids. So actually, what you see here is not a disk of gas. This is the dust in a disk of gas. So this is a little bit misleading, could be misleading. But what I want to show here is the disk of gas, and then solids. And then when you put them together, you have to come with a model that explains formation of some system here. This example of a TRAPPIST-1 system, which is very famous, as you all know probably. So, okay, this is what you have to play with. Now, what is very difficult are the interactions, and so you mentioned in the last talk some of these interactions. So this is a list of some interactions that are important for the formation of planets. So you have solid-solid interactions, as was said before, because, well, solid, they collide one with each other. And so depending on the relative velocity, you can grow in mass or you can fragment, so decrease the mass. It is very important to know what is the structure of a gas disk and how it evolves for different reasons, in particular, as was mentioned before, because solid gas interaction and gas drag is very important for the formation of planets. So, and then you need to know what is the density, for example, or the temperature in a disk if you want to compute what is the gas drag. So this is important for solid gas interaction, also for solid interactions, in particular when you mention pebble accretion, because pebble accretion works because there is gas drag, and so you need to know what is the structure. So other important interactions are planet-disk interactions. As was mentioned in the previous talk, we know, or we suspect, but I think many people are convinced that planets, they are not from where they are now, so they migrate, and they migrate because of angular momentum exchange between the gas disk and the planet. So planet-disk interactions are important if you want to understand what is the distribution of periods of planets. And finally, we need to know what is the internal structure of planet when they form, because this internal structure will govern how much gas is accreted. So will you form a Neptune mass planet or a Jupiter-like planet? And finally, planet-planet interactions are important not only because of gravity, but because the planets that form in the same system, they compete for the accretion of the mass. So they want to accrete same food, same solids, and same gas. And so you need to include this competition in a model. So we have all these processes, and one key question is what is the combined effect of all these processes, and is it the origin of the diversity of a planetary system that we see now? So just to illustrate this, this is a diagram to show that, I mean, this is important to have this interaction between processes. So this is a diagram that shows on this axis you have a mass of a planet in Earth masses, and this is the location in the disk, so sum-major axis. And the color code gives the torque, so what is the interaction between the disk and the planet. So red and violet means a positive torque, so the planet will go outside, outward migration, and blue means inward migration. And the lines, black lines, are places where there is no torque between the disk and the planet. So these two places are where if you put a planet here with this mass at this location, it will migrate outwards. So if you just look at this, then you put a planet of 20 Earth masses at this point, it will go outside, and if you put it at 6 AU, it will go inside. So, and you have the same process here. So if you put the same planet at 12, it will go outside, and at 18, it will go inside. So just naively, from this, you would expect that we should observe Neptune mass planets at 4 and 16 AU, okay? Because that's where they land at result of disk-planet interactions. But we don't observe Neptune mass planet only, well, we don't observe them at 4 and 16 AU, we don't have so many data, but we observe many Neptune mass planets very close, in a place where they should not be, because they should not be stable. So why is it? It's because, in fact, here I only considered the interaction between the disk and the planet, but there are other processes that are important. In particular, the location where you have this zero torque will change because of the evolution of the disk, and the planet will grow, will change its mass. So it's very important to include all these processes, because otherwise you would have a very strange conclusion that we should have Neptune mass planets only at these two locations in the disk. So just to illustrate that it is important to have the interaction between the different processes I've shown before. So you may notice I've still not mentioned population strategies for planets. Now, okay, we are still in the integrated model. We still want to know how we form one single planetary system before trying to go to statistics. So, okay, now how do you compute the formation of planetary systems? So again, you have a full numerical approach that is not possible, but you will just try to follow the dynamical evolution of a set of planetesimals, so many planetesimals. You would have a disk, a model for the gas disk, and then you would evolve the system trying to follow the dynamic of the system. or you have to use some simplifications, because this is, you cannot follow this line, this is too complex. So the integrated model are similar to the stellar evolution model in the sense that you have to make some simplification in order to follow the evolution of such a system over a few million years. So this is just to illustrate this. On this diagram, so you have, this is the distance from the star in AU, that's the time, so this is in a disk, and the color code gives you the eccentricity of planetesimals, okay? And you see you have these very strange features, which are due to the fact that here I put here how, so in this system you have 10 planets that form, and so these are the migration tracks of the planets. And so where you have a planet that is in the disk, the planet will excite planetesimals, that's why you see this, these yellow features. So what is done in the integrated model is that we don't follow, for example, we don't follow the n-body, the evolution of a system of all planetesimals, but we use a statistical model to know what is the evolution of the eccentricity and inclination of planetesimals as a function of time and as a result of the effect of the planets. So basically, we could see 3 levels of integrated models. The first one, which is not possible, so I exclude it, where you would need to follow with n-body the dynamics of planetesimals, and you would need an hydrodynamical model for the disk. So the second level, which is what we have been working on in Bern for 15 years now, is we have a statistical model for the planetesimals. So we don't follow individual planetesimals. We have a statistical model for them, so to know how many planetesimals you have at different locations and what is their dynamics. And we have n-body for the planets, so we really integrate the interaction between planets. We have a semi-analytical disk model for the gas, and then the entire structure of a planet is computed using equations that you may notice are similar to the one from internal structure of a star. And then the last class of model is, again, more simplified. In this case, you don't have any n-body, but you have, this has been developed by Ida and Lin, so in many papers that you may know. So here, you don't really compute the interaction between planets, but you use what we call a statistical n-body to try to know what is the evolution of the system. And the disk model is simplified to some aspect, although this is not so important. And you don't solve for the entire structure of the planet. So the difference between these two is that the second one is very time-consuming, particularly because of the n-body integration. And the second one, the third one is much faster. So what is done in general is that you can do a first exploration of the parameter space with a rapid model, and then when you know that when you think that you have some good model to try to explain some planetary system, you may try with this intermediate complexity model. So again, this is only for one planetary system, okay? I'm not mentioning here population synthesis at all. So I think I will skip this. So, okay, so just to give some more insight in the model that I will use for the next slides. So what is included in this model is the following. So we start with a model where we have a star, we have a disk that you see from the edge here, which is in gray, you have a gas. And then we have planetesimals and we have planets that form inside this disk. So what is included, what processes are included? First, we compute the accretion of planetesimals, because this is what gives rise to the core. So, well, I should say not planetesimals, solids, because this can be done also for pebbles. We also compute the internal structure of the planet, and so this is a sketch of the evolution of the mass of the planet as a function of time. And you may have seen that the planet first inflates and then it shrinks. And so this is because in the first phase, the planet is in contact with the disk, so it fills its heel radius, and then at some point it will contract, and this corresponds to the runaway accretion of gas that was mentioned in the previous talk. We also include, with a statistical model, the computation of the excitation of planetesimals, and this is important because the more the planetesimals are excited, the less they can be accreted by the planet. So excitation depends on, so the dynamical state of planetesimals depend on the excitation by planets, and also on gas drag that tends to damp the E and I of planetesimals. The same gas drag leads to radial drift, which is very important in particular for pebbles, as was mentioned before. So pebbles are well coupled to the gas, so they drift a lot. And then we also include angular momentum exchange between the planet and the disk. So this can lead to migration of the planet outward or inward. So the model that is used here is the same as one I showed before with these color plots. So depending on the structure of the disk, for example, the surface density of gas or the temperature in the disk, you may have outward or inward migration. And finally, of course, there are interactions between planets, so this is done with an body. And just to finish, the gas disk is truncated by magnetic field, and we include irradiation from the star. So irradiation is important because it changes the temperature structure of the disk, which at the end will also change the gas drag, so the excitational planetesimals, then the accretion of planets, then the mass of planets, then the interaction between planets, and so on and so forth. So this is a very, very coupled system. And all the difficulty in this kind of model is to try to have all these different ingredients, all these different processes, and to try to track the interaction between these processes. So just to give an example, this is the formation of planetary systems. So so in this case, you will have the mass of a planet, again, in log scale in Earth masses, and this is the semi-major axis, so 1 AU, 10 AU. The color code will be the fraction of icy planetesimals in the planets. So blue planets mean that they are volatile rich, and red planets are volatile poor. And here you have the time. So we start at the beginning with, so we have one disk. So we have chosen here some mass of a disk, some lifetime of a disk. And then we put 10 planetary embryos in the disk, and then we follow the evolution. So, and okay, just to compare with the solar system, so here you have the Earth, so Neptune and Jupiter. So now if you run the simulation, you see that these are the formation of here, this system. So you see that at the end, you have two planets that are around 3 Jupiter masses. You have one planet here that is very small. One planet is very close to the star and will probably be accreted by the star. And you see that you have a track here. One planet has been ejected. So you have 5 planets. We started with 10. So the 5 other planets are either accreted by some of these 5 guys, or maybe they are just not massive enough so that we don't see them. Because we start with a mass that is like the mass of the moon. So you don't see it on this diagram. So this is just one example of one planetary system. So that is computed with the model I showed before. So what you can do here is then you can try to, that's quite a funny game, you can try to compare this with some real planetary systems. So this is comparison with HG 134987, and you see this is the HD number of the simulation, which is much longer. So we can also have some awful number to designate our simulations. So we start again with 10 planets, 10 planetary embryos, and these are the tracks of the planets, again, mass versus semi-major axis. And so these are the two observed planets, and you see that in this case, we have something that matches more or less what is observed, plus one planet here. So what is interesting here is you could say, well, that's fun. You have something that explains this system. Okay, that's not maybe so interesting to explain this system. Do we predict that there is a third planet? No. So, because what is interesting, here we just compare the mass and semi-major axis of a planet, but if you run this simulation during a long time, you see that it's not stable over hundreds of millions of years. So it's not only, it's not enough to try to reproduce the mass and semi-major axis of a planetary system. You have to reproduce, in principle, all the dynamical state, which is not only the semi-major axis. So what you can do also, it's just something that was not on purpose. Because, okay, you know, observers, they want to find one Earth at 1 AU, and then we found a system with 2 Earths at 1 AU, okay? You have these 2 planets, which is very interesting because they are, so you see that's, okay, 1 Earth at 1 AU, 2 planets. Then what is interesting is that, in fact, this system is stable, and it is stable because the 2 planets are in a 4 to 3 mean-motion resonance. They are not exactly at 1 AU, but this is a stable system. So this is the evolution of the system. So you have a semi-major axis, eccentricity and inclination of planets as a function of time. So you have one planet that is ejected, the outer one, but the 2 planets that are around 1 AU, the 2 Earths, they are stable, at least during 100 million years. So you can see you can play with here with a model. So the only difference between these two models, so this one and this one, are in fact just the initial conditions. So here we assume some disk mass and some disk lifetime, and here we have another disk mass and another disk lifetime. So this gives you some idea of the diversity of planetary systems you can obtain just by changing the initial conditions. So now we can go finally to population synthesis. So, okay, so as I've showed before, so population synthesis, you need two ingredients to do this. You need to have a model to form a planetary system, and then what you do is that you change the initial condition, and then you try to see what is the population of planets you obtain with this model. So again, you need to have a formation and evolution model. So it could be whatever model you can use, in principle, any model that form a planetary system. The only thing is that you need to have a model that is able to track the system from the stage of a disk up to the stage of a planetary system. Then you need to know what are the initial conditions, in particular, what is the distribution of the disk mass, what is the distribution of the disk metallicity, what is the distribution of the lifetime of disk. And so what is done in general is that we use observations. So we know from observation that we have some distribution of these disk properties. And then what we do, we pick at random for every simulation one disk with some properties. And then by putting these two together, we compute the synthetic planet population. So what we think should be, in reality, the population of planets. Then we observe this population. So what we have done up to now was to observe it with radial velocity. So we apply the observational bias. And then we can compare, and then we obtain the synthetic observed population. And then we can compare with the real observed population. Okay? And so when the match is good, then we are happy. And in general, it's not good. And by trying to match the observation with the result of a model, then we can gain knowledge on the different processes that we have in the model. So it basically assumes what I said, that we know perfectly what are the initial conditions. So it assumes that we have a good knowledge of the distribution of the disk properties, which is maybe something that we can discuss because, okay, this is maybe not so sure. So when we have a good solution, then what we have to do is then we use another detection bias. For example, we say, okay, let's take the same kind of the same model, and let's observe it with Kepler. And do we match the observation by Kepler? So if we do this, okay, so just a little movie. So in this case, I run 100 planetary systems. So again, the same diagram, mass, semi-major axis, and all these planets, of course, they are not in the same planetary system. We have 100 planetary systems and 10 planetary seeds per system. And you see that, okay, we form some population of planets. And so if you look again, there's something that is interesting. At some point you start, here you see this planet who are shaking like this. They are in mid-motion resonance with some other planet in the same system. So you just follow the system, and then at the end you have an idea of the state of the system, of a population of planets when the disk of gas has disappeared. So this time when the gas disk has disappeared is not the time when we observe planets, because we observe planets at billions of years. So in principle, what you have to do then is to take these planetary systems and evolve them with a pure n-body for billions of years, which is something that we have done not for billions of years because that's too long, but for 500 million years we have done this. And what is interesting is that it does not change a lot the statistic of planetary systems. So now if you look at so this is just one example of a result of such model. So again, mass, semi-major axis, and now the color code is the fraction of gas in the planet. Okay, blue means gas giant, and red is like terrestrial planets. So this is typically the kind of population that we obtain. So again, what is interesting is that you see that there is a huge diversity of planets, which is also what is observed. Okay, and then what you can do now is to try to really make statistical tests to compare this population of planets with the one that is observed by some different observational ways. For example, if you compare with radial velocity data, so this is the result of Mayer et al. 2011. So this is the distribution of planets as a function of their mass in Earth masses. So this is the minimum mass because this is radial velocity. So in black, you have the raw data, and if you correct from the observational bias that is introduced by radial velocity, you have this red curve. So here you have huge corrections because it's very difficult to observe by radial velocity low mass planets. Actually, it's interesting because this paper is still not published. But if you will see, it's very, very cited in the literature, but you will never find it. And we don't know if it will be published at some point. Okay, so, and then this is the result of the models, and you see, again, a fraction of planets versus the mass. And you see that, okay, that's not so bad. We have this general shape, but we have many planets at low mass, and then it goes down around 20 Earth masses, and then you have less planets. So we have this general shape. Now, it's not totally the same, because we see, for example, here there is a dip in this mass region between 30 and 100 Earth masses that we don't see in the data. So, okay, that's not exactly the same. So this change here in the slope, the fact that we have many planets below 10 to 20 Earth masses is really the signature of a core accretion. It's the fact that when you reach the 10 to 20 Earth masses, we start to accrete gas, and so the planet jumps from this region to very massive planet. So something that can also be done is to compare with Kepler data. So this is a recent paper by Mordassini and Sheen. So what they have done is to compare the radius distribution of planets with the result of the models. So in this diagram you have, so this is a result of a population synthesis. You have a radius of a planet in Earth radii, and that's the distance in AU. And so these are the results of the models. And this map, maybe I show it again. So, okay, these are the result from Kepler, so that's the distribution of radii. And if you plot the result of Kepler in this diagram where you have the size of a planet versus the stellar light intensity relative to the Earth, you have this 2D map, and you see that you have this valley between two populations of planets. So one population at around 2.4 Earth radii and one below 1.5, and there are not so many planets between these two regions. So this is interpreted to be the result of evaporation, and so if you compare the models with the data, so this is assuming that the cores of planets is rocky, and so you see that you have these two populations and no planets in between. And this is assuming that the core of planets are icy. And you see that then in this case we don't match the data. So this shows that probably the cores of Kepler planets should be rocky or volatile poor. Okay, so now I will, so data consistent with a rocky composition. Now, something that I will show now is skip this. So something that is interesting is to try to make predictions. So something that we did, in fact, a long time ago, you don't see the reference, but that's Alibert et al. 2011 unpublished. So again, this, you will never find this paper. It was not published. It was submitted, but we didn't finish the publication. I will explain you later why. So, okay, what you can do is to try to make prediction for microlensing. So for this, you need to know what is the mass distribution of the lenses, because this is the central star for the planetary system. And you also need to know the metallicity of these stars. So what we have done was to take the probability of different masses. This was from Dominique 2006. So this is the mass distribution of the lenses of the central star of the planetary system that should be observed by microlensing when you look towards the center of the galaxy. And then what we have done was to use the Besançon model to have the distribution of the metallicity of the stars. So here is the metallicity, and that's the distribution. So the solid line is the total distribution of metallicity. The two other lines are one for the bulge and one for the disk. So if you combine this with some population, some model to form planets, then you can compute the theoretical length population, including the mass and metallicity distribution. So for this, you see that we have stars of different masses from 0.1 up to 2 Earth masses. So what we have done first was to compute formation models for different stellar masses. So from 0.1 to 2 solar masses, and as you said before, Kathleen, you see that there is a strong effect of a central star on the population of planets. So this is again mass versus the major axis. And when you go to low mass stars to high mass stars, you see that you really change drastically the population of planets. So I just want to say, so this is from 2011, this unpublished paper. So these are planets with only one model with only one planet. So these are not the last models. But nevertheless, what you can do is to combine these models with the distribution of a stellar mass, and then you get this population of planets. So this is the population that should be observed by microlensing if you believe that this is the distribution of the masses of stars, and of course if you believe the formation model. So then you can observe this population with well, in this case it was from we used the observational bias from the planet collaboration. And then you have in red the population of planets that could be observed by this observational bias. And finally, you can compare with data. So at the time, we had only 12 microlensing planets, and then these are the planets in blue that compare more or less well with the red planets. So again, this paper is not published. Why? So the problem that we saw is that, in fact, if you want to do this comparison, you need to be sure that the observational bias that you use here is the one that has been used, in quote, to observe these planets. And this was not the case at the time, because all these planets come from different, you see in the table here, you have Moa and Ogle planets, so they are not observed with the same observational bias. So it's very difficult, in fact, in this case, to really compare the data and the models. And so one hope that we have is that in the future, in particular with WFIRST, we hope that there will be a good match between the list of observed planets and the observational bias that has been used to detect these planets. And then, in this case, you can make a real statistical comparison. So, okay, in this case, just for this model, this is a comparison between the distribution of semi-major axis of planets and the data. So this, this line is the result of the observed planets, and this is the result of the mass function. So, okay, I don't want to spend too much time on this because, again, it's very difficult in this case to compare this observation and this model because we don't really know what is the observational bias that is associated with these observations. Okay, so I have 12 minutes now to come back on something that is more related to the formation of planets. So, as was said during the previous talk, so one big problem in the formation of planets by planetesimal accretion is the time scale of formation. So, if you take some standard model, then you see that the formation of Jupiter is very difficult, and Uranus and Neptune are very difficult to form because you never reach a critical core mass early enough. So one thing that was proposed, as was explained before, is to use pebble accretion. And pebble accretion is it's clear that it's very rapid accretion. So what I will try to do now in the following is try to compare so what are the outcome of these two models? So either assuming that you have a mass, the solids are pebbles, or the solids are planetesimals. So again, the difference between these two models lie in the efficiency of converting dust to big bodies. So in planetesimal-based model, the mass is in planetesimals of few kilometers in size. And in pebble-based model, the mass is in pebble, so centimeter size bodies. So I will not come back to the planetesimal-based model because all the things that I showed before in population sciences were based on this pebble planetesimal accretion model. So if you summarize what are the pros and cons of the model, so as we have seen on the mass function of planet, it is quite similar to the observed one, so that's a good thing. If you look at the disk size and the disk mass that you need in order to reproduce this data, they are similar to observations, that's good. One very big problem, and I think that's the biggest problem of planetesimal accretion model, is that it works only if you have low mass planetesimals. So it only works if you have kilometer-sized planetesimals, maybe 3, 5 kilometers, 10, but more it's very difficult. And the reason for this is that if you have big planetesimals, let's say 100 kilometers in size, then they are excited by forming planets. And they are so big that they don't suffer gas drag. So gas drag is very inefficient for 100 kilometer planetesimals. So these big planetesimals, they are excited. And so when they are excited, they are very difficult to accrete because they have a very large relative velocity with a planet. So gravity is not very efficient when you have very large relative velocity. So if you want that you accrete efficiently planetesimals, you need to assume that they are small mass, small size, so kilometer. But now if you remember what was shown in the previous talk, models that form planetesimals, they typically end up with planetesimals that are hundreds of kilometers in size. So here we have a big problem. So one way that you could solve this is that you may form big planetesimals, 100 kilometers, and then these planetesimals could collide and fragment and form smaller planetesimals. But that's just an idea and it has not been tested very well. And the second problem is the formation of planets at large distance. So this is this timescale problem. So the reason for this is that the accretional planetesimal scales with the Keplerian frequency. So when you are at 50 or 100 AU where we observe some planets, it's very long to form these planets. And so forming in the framework of the core accretion model with planetesimals a planet at 50 or 100 AU is extremely challenging and practically doesn't work. So to explain these models, you have to assume something else, like maybe these planets have been ejected or there is outward migration or maybe they are just formed with another mechanism. So let's move to pebble-based models. So pebble-based models, they are, pebble-based, if I remember the first paper is 2010, so it's quite recent. So the model that I will show now, they have less physics inside in particular. What I will show, models are based on the formation of only one planet. So there is no planet-planet interaction between in these models. So one very popular model is the one of Beach et al., so 2015. So this is one result of their model. So this is a complicated diagram that I will explain now. So you have on this axis the formation time. So when you assume you have a planet that starts its formation, and that's the location of the planet. So where you assume that you start the formation of a planet. And then this color, what you have here is the final mass of a planet. So if you start a planet at 20 AU and at 1 million years, you are here and you see that you have at the end a planet that is red, so maybe 3 Jupiter masses, okay? Then this line is the location, the final location of a planet. So if you take this example, you have a planet of 3 Jupiter mass at 0.5 AU, okay? So, this is the result of one particular model that we have developed. So, and this is based on the accretion of pebbles. Something that is interesting is this line, which is the origin of pebbles as a function of time. So, the pebble, they drift very fast in the disk. And so if you start your formation at 20 AU, you see that in fact, the pebble you will accrete at 20 AU, they have been formed maybe at, 70, 80 AU. So because they drift very fast. And one consequence of this is that since you accrete material that has been formed very far in the disk, it should be volatile rich. So pebble accretion in general predict that planets are volatile rich, which has some implication on the habitability of planets in particular. So something that is interesting that you can see here is you may wonder, okay, what about the formation of Neptune mass planets? So Neptune are green in this scale, and Neptune mass planets are around 10 AU. And if you look at this, and these two lines, the blue line that you have here is the line where you have 10% of the mass in gas. And the white line is the place where you have 50% of the mass in gas. So Neptune is around 20% of the mass in gas, so it should be between these two lines. So if you want to be green and between the blue and the white line and around 10 AU, 10 to 20 AU, you see that it's a very narrow range where you have to start the formation of a planet. So you basically have to start between 15 and 20 AU at 2.5 million years. Okay, and otherwise you don't form Neptune mass planet. So then if you take this kind of model and you look at the distribution of planets that are formed, then you don't have many Neptune mass planets and you have no hot Neptune. And this is a problem because we know that there are many hot Neptunes that are observed. So, the outcome of pebble-based models, so one very nice thing from pebble-based model is that there is no time scale problem. In fact, the formation of planet is very rapid. So in general, when you run the model, you have difficulties to have small mass planets, so you have kind of an inverse timescale problem. It's forming planets too fast. Something that is a little bit disturbing is that you need to have very big disk in radius, just because pebbles, they drift so fast that if you want to sustain the flux of pebbles for a couple of million years, you have to produce them very far in the disk. You need to have a disk that are very big, 100 of AUs, which is maybe a little bit of a problem. And the formation of Neptune's mass planet is very unlikely, at least in the model I've showed. So it doesn't mean that it is not possible in the case of pebble accretion, but from the model that you have now on the market, it's a little bit a problem. The last thing I want to mention is that a very big problem is that pebbles, they are destroyed in the planetary envelope. So if you think to this, if you take, although it's not a very good comparison, but if you take the Earth and you throw a little pebble, so 10 centimeter ball of ice toward the Earth, then what will happen is that this ball of ice will be destroyed in the envelope. So it will not reach the Earth. So when you accrete pebbles, so you have this kind of situation, you have a core and you have the envelope of gas, and then accreted pebbles, they interact with the envelope, and at some point they start to be destroyed. So what you can do, you can compute what is the mass of the core you need so that you have enough envelope to destroy the pebble, and it turns out that it is a couple of Earth masses. So when you have a planetary mass that is larger than 1 to 2 Earth masses, then the envelope is big enough to destroy pebbles, and so you don't add the mass of solids to the core, but you distribute the mass of solids in the envelope. So what you do is that you pollute the envelope. You increase the mean molecular weight of the envelope, and you don't increase the mass of the core. Okay, you could say, well, that's not a big problem, because if I put more and more pebbles, I will increase the pollution of the envelope. At some point, maybe this heavy element will condense again, and then they will sink down to the core. But the problem is that we know from some recent simulation by Chris Hormel that the envelope of a planet is not a closed system. And there is exchange. There is gas coming from the disk that goes inside the envelope, and then there is gas coming from the envelope that goes back to the disk. So we have this thing that is called a replenishment process. So you continuously replace the gas of the envelope by something coming from the disk. So it means that if you have this process that is more rapid than the pollution due to the accretion of pebbles, then you can see that you will never be able to pollute the envelope, because as soon as you put some matter in the envelope of a planet, then this matter is lost because of this replenishment process. So if you use the estimation like Chris Hormel and you try to see when is this process more rapid than this pollution, you see that inside 10 AU, this process is more rapid. So it means that if you summarize this, if we take a planet that is inside 10 AU, that grows by accretion of pebbles, then when you have a core mass that reach 1 to 2 Earth masses, then the pebbles, they don't reach the core. So you don't increase the mass of the core. Instead, you try to deposit this mass in the envelope. But because there is exchange with the disk, when you are inside 10 AU, you cannot accumulate the heavy element in the envelope. So it means that you have your heavy element that come from the pebble, they are deposited in the envelope, and then the envelope is lost. So you cannot increase the total mass of heavy elements in the planet. So the only way you have to try to increase the mass of the planet is then to accrete gas. But at 1 to 2 Earth masses, in fact, the accretion of gas is very inefficient. So it means that in this case, you cannot increase the amount of solids you have in the planet. You cannot increase the amount of gas. So you cannot grow the planet beyond 1 to 2 Earth masses if you are inside 10 AU. So I think that's something that is a big problem for pebble accretion. And in fact, this is very completely linked with pebble accretion, because all this process comes from the gas drag, from the interaction between pebbles and gas. And pebble accretion works because there is the interaction between gas and pebbles. So you cannot have pebble accretion without gas drag. So, and gas drag may be a very difficult process when you want to form planet beyond a couple of Earth masses. So, okay, this is something that is now, okay, I just want to emphasize that this result is based on some estimation of this replenishment timescale of the planetary envelope. Maybe there are things that we don't totally understand in this process, but this is something that shows that maybe I'm not so sure if pebble accretion is a solution to planet formation, and then we have a big problem, because it seems we have no solution for planet formation, but we know that planet exists. So I will have 24 seconds to conclude. So one thing I would like that you remember is that you should not mix population synthesis models and formation model of planetary systems. These are different things. If you want to do population synthesis, you first need to have a model that is able to explain the formation of a planetary system, and then you need to have some knowledge on the initial conditions, properties of a disk in particular. When you have these two, then you can use population synthesis model to have a global picture of planet formation, trying to see what are the important processes in planet formation, and then you can then compare the observation. Something that is very important, I would like to emphasize, is you need to know what is the observational bias that is associated with some kind of observations. In particular, blind observations are much better because they avoid the observer bias. And in fact, this observer bias is the fact that, when you're an observer, you want to observe a planet, and then you want to publish a planet. And so when you see that there is maybe a planet, what you do is that you observe more and more and more and more, and then you get the planet. And so then this is a nightmare to include in the model because you cannot be in the mind of the observer. So the survey that have some very well-defined strategy are much better to try to constrain the observation, and I hope that a microlensing survey will be able to do this. And so, and the last point is that I've not really emphasized this, but it was said in the previous talk. Microlensing probes the part of a mass semigenesis diagram that is very different from transit and radiant velocity. So it's a very nice and complementary constraint to planet formation. And so I hope that we will have at some point a set of microlensing planets with the associated observational bias to really constrain the models. And I'm too late, so I stop now. Thank you. Well, you can take basically what you want, provided that the difficulty is that you need to know what are the properties of a disk if you change the mass of a star. And that's something that is not well understood from the observation. So, so in particular, we know that for low mass stars, the mass of a disk is probably smaller. So people argue it could be maybe a linear scaling. What is not so clear is what is the lifetime of a disk around low mass stars. People think that the lifetime is longer. They are scaling like it's inversely proportional to the mass of a star, but this is really debated. So this is something that is very important because what we have seen running this kind of model is that the properties of the disk are one of the key if you want to have at the end some population of the planets. So in the model, you can change the mass of a star, but you need to be careful to change everything consistently. But basically what you said in your talk, you have to be careful. You cannot just change it in one part of the model. So what we are now doing is that, so before being able to compare, so what I've showed before was based on old models where you have only one planet forming in the disk. So what we are now running is to run the same model but with multiplanetary systems. So we have more than one planet. What we do now is we run this model for all kind of stars, so between 0.1 and 2 solar masses. And then when this will be done, what we plan to do is to combine them and then compare. So, but it takes some time on the computation. Yeah. I don't know, soon. As soon as possible, I would say. But what we need for this is to have a distribution of stellar masses and stellar metallicity.
Well, it's whatever's in the galaxy.
Sorry?
It's whatever's in the galaxy.
Yeah, but okay, we need to know this. If we know this, that's just a question of computation, and then it's possible to do it. So we are not far, I would say. I would say we are close, very close. So yeah, I hope this year we can have some models. But that's absolutely clear that there's very simplified vision to say that's one or the other. My impression is that pebble accretion alone cannot work. But I really think that it has an effect at some point during the formation. And I really think that combining both could really be the key to explain some of the data we have, in particular for the solar system. So, but, I mean, we can discuss this later, but I think, yeah, it's something that will be done soon.